Hello, in this video I'm going to be going over the Carnot cycle and the equations that involve it and how to derive them. So essentially the Carnot cycle is for ideal gases. And essentially what it will look like is you have a pressure volume graph, and we will make 4 different points, connect them all, and we'll label them as so. This is A, B, C, D. So essentially between A and B, I'm going to write this over a bit more so I have more room. From A to B, this is adiabatic compression. So essentially what adiabatic compression means is that the surroundings do work on the system. And then we have from B to C right here. This is isothermal expansion. And what happens in this is that heat is absorbed. Then from C to D, we have adiabatic expansion. And what happens in this is that it expands due to a decrease in pressure, and it does work on the surroundings. And then finally, we have from D to A, which is isothermal compression. And what you can guess here is that it loses heat, the opposite of B to C. Now, the important thing to know is that the Carnot cycle is essentially saying that the change in internal energy of all these things is 0. You don't lose any to heat between all of these, nor work from all of these. So essentially from this, we can also say, from moving work to the left side of the equation, we can say that the heat equals the negative work. I don't like how I capitalize that, so I'm changing it. So now we can describe essentially what adiabatic means specifically. And if it has adiabatic in front of it, in other words, it means that there is no heat transfer. However, for isothermal, heat is transferred. So now we can specifically start looking at the equations that correspond to each of these two processes. So we'll take a look at isothermal first. For isothermal, this is reversible, and we are specifically going to look at the work done. So the work is Q minus delta U. However, we know from up here that delta U must be 0. So we can now say that this is the same as saying Q minus 0, which means the work equals Q. And again, this is 0 because there is no change in internal energy in isothermal. So now we can go ahead and bring this down here so we can see it better. We have W equals Q. So we know du equals small amount of heat minus PdV. So this is the same as saying Q minus, and we have an integral, and we'll say from B to C. So then this, and then this is pretty much derived from simplifying this more. Then this will simplify even more to was essentially Q minus RT and natural log of VC over VB. And we can, if you really want to look at it, we could say specifically QH equals RT natural log. And now this is where you have to look specifically, as the higher line will be the hotter temperature. So since we want QH here, it will be from B to C. So just like here, we will have VC over VB. However, if we want QC, we will do RT natural log, and we'll look here, and we'll have VD over VA. Actually, I think I switched those around. So now we will move on to the adiabatic. And this is also reversible. So for the adiabatic, we will have a similar equation as above, right? Where is it? I can't find it right now, but we will have du equals, oh, it's here, but we are going to go ahead and plug in the RT over V. So we have small amount of heat minus RT over V, and we'll still have the dV. Now in an adiabatic, we have Q equals 0. So if we take the integral of du, we'll have a negative here because 0 is plugged in here. And we'll take the integral of RT over V dV. And we will get du equals CV dt. Well, this is not what we'll get, but this will be a substitution for here because we're trying to simplify it. It will make sense at the end, so we'll plug in CV dt here for the integral. Well, I'll rewrite it to make it look easier to follow. So we have CV dt, and this equals negative RT over V dV. And CV is heat capacity. So now essentially what we'll end up getting is integral dt over t equals negative R over CV. It's going to be hard to make this V small. Negative R over CV integral dV over V. Now essentially how we get this right here is because R is constant, CV is constant. So we divided CV by dt to get dt on itself and bring it over here. And we divide t, this side of the equation by t to get over here with the dt. So by doing that, we get this. And what these will equal is natural log of T2 over T1 on this side equals negative R over CV times the natural log of V2 over V1. And that is essentially how you derive the Carnot cycle equations.